Having previously dealt with oscillations, we now want to talk about the nature of waves themselves. And in this particular slide, this shows a mechanical wave being a wave set up in a medium such as a string or solid object or fluid, and here we have an electromagnetic wave, which we'll talk about in more detail later. Still, a wave like this is generated by an oscillating electron or other charged particle, giving an electromagnetic wave, E and B. Now when we talk about our waves, we're really talking about anything that's in simple harmonic motion. Here we have, as per our discussion on oscillations, a high frequency wave. Here we can see a short period, and we can see the same amplitude here as we see in the low frequency wave. But here we have a short period and a long period. The frequency, of course, being the inverse of the period of our wave, 1 over t. Meaning that throughout our discussion we can really characterize the behavior of a wave, or indeed its very nature, by talking about period, wavelength, or frequency. The wavelength being the distance between repeating points, successive troughs or peaks, and the frequency being the number of waves that pass a point in a particular time interval, usually expressed as per second or hertz. So as shown here, our frequency is given as 1 cycle per second. That can be inverse seconds or a hertz. And of course, as we just said, our frequency and wavelength are essentially interrelated. So a long wavelength wave tends to have low frequency and therefore deliver less energy per unit time, as fewer waves are impinging upon a particular point per unit time. So long wavelength equals low frequency equals low energy. A short wavelength gives us higher frequency and gives us higher energy. So what is a wave? A wave is referred to as a rhythmic disturbance that transfers energy. Now this can be mechanical, as said before, or could be electromagnetic. Here we're going to deal mostly with mechanical waves, and we'll move into electromagnetic waves later in the class. But you should remember this information for later on. But the thing that is the same is all waves are made by something that vibrates. So when we talk about mechanical waves, what we mean is something that needs matter, some kind of medium to move through. Something like sound means vibrating air molecules. It could also move through water. You could look at seismic waves coming from earthquakes. As an earthquake occurs, an enormous energy release vibrates the ground, and waves move through the ground. There are two types of mechanical waves. One being transverse, which is the typical kind of sinusoidal wave that we see in graphs showing a crest and a trough. The other is longitudinal. This is a compressional wave. So here we have a compression, and then we have a rarefaction, as it's called, which is essentially an expansion, and then a subsequent compression. So as said before, our wavelength has an inverse relationship to the frequency. That means our velocity depends on the type of wave and the type of medium. This means that sound is faster, for instance, in a more dense medium and in higher temperatures. Light is slower in a more dense medium, but faster in a vacuum. So if we take the speed of sound, if we pass sound waves through air and vibrate air molecules, this will have the effect of actually being slower than if we vibrate the molecules in a fluid such as water, something much denser. Now the equation for the speed of a wave is v equals f lambda. Its frequency multiplied by its wavelength equals the velocity of the wave, how quickly that wave will propagate. The amplitude, of course, was the size, which is related to the energy carried per wave. Now, as said before, we have a transverse and a longitudinal case. The transverse case, shown here, of this oscillator bouncing up and down, is really measured by how high above or below the center zero or nodal line our oscillator goes. Our longitudinal wave, shown here in a better sense than the previous spring, shows what happens as a vibrator is moved back and forth. So here, this object here is thrust forward, compressing this spring. This causes a movement of this particle, which compresses this spring. And this compression wave is moved down the line by compressions and rarefactions from one end to the other. Now, even though we're looking at two different types of wave, if we look at this particular wave and how it's propagated, it can still be plotted essentially in the form of a transverse wave. This can be a little confusing, and you do have to take note of what type of wave you are dealing with, as they will still follow the same mathematical relations for either case. So in terms of our sinusoidal travelling wave here, these are our guiding equations. Here we have v equals lambda over t, our wavelength, our period, our velocity. This is a simple rearrangement of the same formula. A disturbance will travel with some velocity and will travel a distance of lambda in one period t, hence v is lambda over t. If we want to find the velocity v, we can take the frequency and multiply it by lambda. So let's talk a little bit about the actual nature of waves themselves. And this is one of the fundamental equations that we employ when we talk about waves. Y, or this can sometimes be seen as A, the amplitude of our wave, Y, the actual displacement of our wave, is the amplitude, Ym or Ymax. So here is our displacement at any one point in the wave. Here is our amplitude. We have our sine function showing that this is a repeating pattern, a harmonic term, and inside our oscillating term we have the phase of the wave. Inside this phase we have time, we have the angular frequency, which is given by omega, or f equals 1 over t for the linear frequency. We have position, and we have what's referred to as the angular wave number, k equals 2 pi over lambda, 2 pi being one complete cycle of our wave, lambda being the wavelength itself. And these are useful terms to note down while we look at this particular equation. Displacement, what is the displacement at any particular point in our wave, is equal to the amplitude times sine kx minus omega t. It is then a task to find out what is omega, what is k, from the given values, substitute in, and solve for the displacement in many cases. So we're really moving towards a mathematical description of our wave. So again, here's another wave with amplitude and negative amplitude here, both equal, so no damping or any other effects here. So if we take a quick shot of our wave at any particular time, the displacement, essentially y, will be a cos 2 pi x over lambda. If we look at the wave motion and say it's moving to the right of this particular diagram with a velocity v, then we'll say that our displacement at some point will be the amplitude times cos 2 pi x minus vt now. So this really comes from our equations of motion divided by our lambda. And this really allows us to define that new quantity that we referred to before, which was our wave number. k equals 2 pi over lambda. This is the equation we essentially saw before, substituting in for our wave number here, and we'll end up with v equals f lambda, which will be 2 pi f over k, or omega over k. Substituting this in, we'll see that y is equal to a cos kx minus omega t. So in our wave motion, y is a function of both x and t. So if we take a look at our wave, we can say here that the curvature of a string, so here we're setting up a system where the wave is essentially moving down a mechanical medium, such as a string. The curvature of the string is a maximum right here at the top, where particle acceleration during our simple harmonic motion is also a maximum. Curvature of the string here, if this was, you can imagine how this string would look, is essentially 0. So the acceleration of our particle is 0. So any point on the string here that's bouncing up and down, we're going to look at maximum acceleration here, minimum acceleration here, and again another maximum but in the opposite direction here. And this is what leads to something called the wave equation. Now you do not need this derivation, but I do like to show where derivations come from, so equations do not appear as if by magic. So if we look at the displacement of a part of the string curvature will be this, d squared y by dx squared. So the movement of any part of the string can be looked at by the position of the y and x coordinates with time. The acceleration of the particle, essentially in the y direction here, will be d squared y by dt squared, the second differential of essentially the position with respect to time. So this means that d squared y by dx squared is proportional to d squared y by dt squared, as we're seeing here. Now if we go back to our original equation, y here is equal to a cos kx omega t. We know this is true. So dy by dx, essentially the displacement in the y direction, is equal to negative ka sine kx minus omega t. Taking the differential here, we will end up with negative k squared a cos kx omega t. And then saying dy by dt now will be this, omega a sine kx minus omega t. The second differential, d squared y by dt squared, will be this in terms of omega, a and k. And that means we will end up, if we put it all together, with d squared y by dx squared. So putting these results together, we'll end up with 1 over v squared d squared y by dt squared. You can convince yourself of this particular final step or take a look in the book, but this is an equation that will come back a lot in terms of how waves behave. And this applies to all wave motion, not just the case of a sinusoidal wave on a string like this. This is essentially the ratio of the acceleration to the actual particulate motion and applies to everything. Now if we continue our discussion of the wave speed on a string, now in the x direction we can say this. We can look at the period of a small element of motion on our string. So finally, we will end up with this value, d squared y by dx squared. Now this has a mu value. This is essentially the density of a piece of the string, the mass per unit area, which will give us v equals root t over mu. Now that value is going to come back again later, so please remember that. And eventually, here's our normal equation. So what can you do with this wave function? This is all well and good that I've given you this wave equation, but what's really the point? Well, the wave equation really is a function that tells you exactly how your wave will behave. And this is the kind of thing you have to solve in generating electromagnetic radiation, or the response of a building or item to a particular vibration. So the question here is, we have a function y, and that's equal to x squared plus v squared t squared. Now, is this a wave or not? If it's a wave, then this particular function will be a solution to our wave equation. So we just saw in our previous case the proof of the wave equation, and essentially we have to do the same thing. So here we've got y is equal to x squared plus v squared t squared. dy by dx here will give us 2x. A partial derivative d squared y by dx squared will give us 2. Now let's look at the derivatives with respect to time. dy by dt will give us v squared 2t, and d squared y by dt squared will give us 2v squared. Now let's compare that to our standard wave equation and substitute in. Here we have d squared y by dx squared, that's this result. We have essentially d squared y by dt squared here, which is 2v squared. So let's substitute in. So we will end up with 2 is equal to 1 over v squared times 2v squared. Our v squareds will cancel and give us a value of 2 if we look at this side of the equation. Consequently, this is a solution of the wave equation. So if we're looking at the speed of a wave, we've just characterized the actual nature of a wave. Now let's look at, say, the speed of a wave. The velocity of a wave is given by this. V is essentially lambda over t, or lambda f. These are two equations we've seen previously. Or omega, the angular velocity of our system, the angular frequency, more accurately when we're dealing with a wave, divided by k, the wave number. So let's take a look at a problem here. Here we have a standard sine wave. It's traveling in the positive x direction with an amplitude of 15 centimeters. It has a wavelength of 40 centimeters and a frequency of 8 Hertz. The vertical position of an element of the medium at t equals 0 and x equals 0 is also 15 centimeters. So we know what the vertical position is at t equals 0, and that we should see from this diagram. Here's our 15 centimeter point, so we know at what amplitude our wave is starting its travel. So our question is, what is the wave number here, the period, the angular frequency, and finally the speed of the wave? So let's characterize this wave completely. First of all, this question wants to know the wave number. What is k? Our wave number is defined as 2 pi over lambda. We know that 2 pi is in radians. You could convert lambda to meters if you wished. I'm going to stay consistent with this particular example. Little unusual for me, but I want to stay with this. Substituting in 2 pi over 40 centimeters essentially, and then I'm going to convert it in the final step. So 40 is 40 times 10 to the minus 2 meters essentially, will give us 15.7 radians per meter. So simply applying the equation. Again, the period. Here, period is 1 over frequency. Always look at exactly what you have. And you do have a frequency of 8 Hertz that you can utilize, which is 1 over 8 inverse seconds, which will give you 0.125 seconds. Our next point wants the angular frequency. What is omega? Omega is always 2 pi f, and as you can use this equation, you can kind of see how we've actually developed this particular problem. we've gone from period into angular frequency, and now we're completing our discussion of all of the various properties of the wave. So omega is 2 pi f. This is 2 pi times 8 seconds, which gives us 50.3 radians per second. Make sure that you're calculating everything in radians. Finally, the speed of the wave, which is v equals f lambda, is going to give us 40 centimeters times 8 seconds, or converted 3.2 meters per second. The other thing we can look at is phase constant. The phase constant phi is really telling us at what phase our wave is at. And we can write a general expression for our wave function of y equals ym sine kx minus omega t. We're going to generalize this even further. So here we can substitute in our 15 centimeters, our x equals 0, t equals 0, and essentially we'll end up with 15 is equal to 15 sine phi. Sine of phi, of course, here we're going to say is equal to 1 if it's equal to unity. This means phi is pi over 2 radians. This means y is a sine kx minus omega t, the equation we already know from above, plus this phi value, plus this phase. This gives us a cos kx minus omega t. So y essentially becomes 0.15 cos 15.7 minus 50.3. When we look at our wave function, the usual wave function is essentially a sine kx minus omega t. We have some transverse speed and an acceleration. So dy by dt essentially is the velocity of our wave, will be negative at omega a cos kx minus omega t. Or a, if we take the second derivative of the position or the first derivative of the velocity in the x direction, will be negative omega squared a sine kx minus omega t, with our identity switching essentially as we differentiate. This means that the maximum velocity, essentially, if you don't want to go through this procedure each time, will be equal to omega a, and the maximum acceleration will be equal to omega squared a. So when we're dealing with sinusoidal waves on a string, the magnitude of the force acting on the string will be this, which is essentially 2t theta, if we're looking at small angles. The mass is mu delta s, that's the displacement, times essentially the mass per unit length of our particular string. So mu is mass per unit length, so m is mu times delta s. Substituting in, this becomes 2 mu r theta. If we look at our forces, we can eventually derive a force or tension in the string of mu v squared. So if we want to find a velocity in our string in terms of its tension and its mass per unit length, we will end up with this equation. Again, I would not ask you to derive this equation, but the result is a very important one. So let's use this result in a calculation. Let's take a look at the speed of a pulse through a string. Here we have a uniform string of mass 0.3 kilograms and length 6 meters. The string passes over a pulley supporting a 2 kilogram object. So to make things clear, we have two masses here, the mass of the string of 0.3 kilograms and the mass hanging from the string of 2 kilograms. we're going to find the speed of a pulse that travels along the string. And you may have seen a setup very similar to this previously in mechanics. So find the speed of a pulse travelling along the string. First of all, let's think about the forces involved. The forces in the y direction here will be T, the tension acting in the string, and mg, the mass of the block times gravity. This means the forces in the y direction will be T minus mg. If these are equal to one another, which they should be if this is hanging in an equilibrated fashion, then T minus mg will equal 0. Solving for the tension in the string, we'll get T is equal to mg. Now that we have T, we can go back to our previous equation. V equals root of T over mu for the velocity of our wave. Now remember, T is the tension that we've just found here, mg, and mu is essentially m over L. Consequently, if we substitute into this formula, because this is m over L, the L will come to the top here as it's divided twice, and we will end up with mgl over m. Of course, this is mass of block and mass of string, so these masses do not cancel, a very common error in a problem like this. Substituting in, 2 kilograms, 9.8 meters per second, 6 meters, and 0.3 kilograms for the mass of the string, and we will get 19.8 meters per second. Another definition that we can make is that of the power of a wave. We've just seen that a wave will have a specific velocity in a medium. If it has a velocity, it will have a kinetic energy. Consequently, the average rate at which kinetic and potential energy is transmitted by the wave will actually come from a differential of our wave number. The average power will be 2 dk by dt. Now, I'm not going to show the derivation here or go through this, but what you do need to know is what is the result. And the result itself is a fairly long equation, but not a particularly complicated one. So the average power of a wave is 1/2 mu v omega squared times the amplitude, ym here, squared, where mu is our string density, m over L again, omega is the angular frequency, v the velocity, and y the amplitude. Now usually this equation is just used outright to find power. Let's take a look at an example of how to use this particular equation. So if we have a string and it has a mu of 5 times 10 to the minus 2 kilograms per meter, so it's already in the right units here, and it's under a tension of 80 newtons. How much power must be supplied to the string to generate sinusoidal waves at a frequency of 60 Hz and an amplitude of 6 centimeters? We do have a mix here of meters and centimeters, so we must be a little bit careful in how we proceed. But generally, when faced with a question like this, you should use the usual shopping list method that we use throughout our problems. State mu, state 80 newtons as a tension, state the frequency, and state the amplitude. That should lead you to the conclusion that we're looking at this power equation. How much power must be supplied is also a clue. Of course, this could be given a slightly different form of 1/2 omega squared a squared v. I've just substituted a in here for ym. I just kind of prefer a as amplitude. It seems to make more sense to me. The book uses ym. You may use any variable you want as long as you're correct. We are of course substituting in for v to say root t over mu. We could simplify this even further, even though we have t and mu and could proceed at this point. We can simplify this a little bit further and get rid of our factor of 1/2 here, and this will give us P is equal to 2 pi squared 60 by 0.6 squared, which is times root of 0.05 times 80 newtons. You could of course evaluate at this particular point here, given that you have all of the variables, and give ourselves 512 watts. This is a power, so it will be quoted in watts. Now here of course the 6 centimeters has been converted into meters. You would have to do that given that mu here is given in meters and your force is given in newtons. So make sure you're in the right unit regimes. So just a quick reminder on the nature of waves. We had our displacement, of course. We had our amplitude of our wave being ym or a. We have our phase term and of course the oscillation term, which encompasses our harmonic. We have our time, angular frequency, the displacement position x of course, and we have angular wave number. K is equal to 2 pi over lambda. We're also armed with omega being 2 pi over t, and of course the linear frequency 1 over t being omega over 2 pi. It's worth writing this equation down and all of the associated variables that go with it, such as the wave number, omega, and f. Now, when we look at waves, this is the fundamental equation for defining the nature of our wave. If we're to look at the interaction of two waves, we will have two such equations. One, a y equation, a displacement equation for wave 1, and a displacement equation for wave 2. Waves are usually travelling in some direction. Usually we define in the x direction and are incident on one another. Here we're going to deal with head-on collisions of two waves and how they interact in what we refer to as interference. Now you can experience interference in sort of everyday life, from a cell phone to a TV or any other type of device. Usually now in the digital era, this involves our signal breaking up, pausing or slowing down, or stopping completely. In days gone by, interference of waves usually resulted in a more of a static sound or visual response in a TV or a radio. But still, the principle is the same. We're looking at waves interacting. We can also look at mechanical waves interacting. And here we've got two mechanical waves set up in a rope. This person here is flicking this rope and causing a mechanical wave to move from the left to the right. This wave is a relatively high amplitude. Person 2 here is flicking this rope and generating a small amplitude wave going from right to left. These waves will interact and hit each other head on. As the two are in the same amplitude here, both in the positive y direction, you will end up with these two waves adding together as they travel, creating a wave of greater amplitude, equal to the amplitude of these two waves. So you'll add these two together and that'll give the amplitude of this wave. The waves then continue, this pulse going on its journey towards the end of the rope where it will probably dissipate into the person's hand, and this wave going to the end of this rope. And that means our waves will interact as they travel. So here we've got two waves coming together and interacting from the left and the right. As they interact, their amplitudes are added together, creating a wave of a new amplitude very briefly. When these amplitudes come together and are added, they're referred to as the principle of superposition. And by superposition, we mean if here's our zero line, our red and yellow wave will come in and interact. The displacements in the y direction at each point in the wave will be added together. In this case, these waves are perfectly in phase, meaning that the red dotted line and the yellow line will add together, creating a wave of greater amplitude, given by the blue dashed wave. That's superposition. In this case, our two waves come together perfectly in phase, the positive displacement adding to the positive displacement, and our negative displacement, adding to our negative displacement. This will simply give us a wave that is twice the amplitude of the original two waves. When our waves are in phase and interfere with one another, this is resulting in what's called constructive interference. Here we have wave 1 coming in the blue curve, and wave 2 as the yellow line. As the two come together, they will be added to give us wave 1 plus wave 2. If these were sound waves that were constructively interfering, you would have two low volume waves come together and produce one louder wave. Now, as well as constructive interference, we can have the opposite, which is referred to as destructive interference. Now here we have two waves that are completely 180 degrees out of phase, or a factor of pi out of phase. As the two waves come together, the red and the yellow, you'll see that the lowest point here, the lowest amplitude on this wave, equals the highest amplitude on the corresponding yellow wave. As these two interact, this will result in a reduction of each point on each wave, giving us a complete negation of this wave. This wave will completely cancel one another out. The interaction of these waves gives us perfect destructive interference and gives us an overall displacement of 0. This is referred to as destructive interference. If you have two waves that are exactly 180 degrees or pi out of phase with one another here, you will end up with a situation where they cancel out completely and our total wave becomes 0 amplitude. That is our destructive case. This is a destructive interference case. So if the waves are out of phase, here we have the lowest point of wave 2 coinciding with the highest point of wave 1. As these two are added together, this will result in a reduced overall amplitude for wave 1 plus wave 2. And we can see this here. Here are waves essentially interacting, the red and blue waves. As they interact, what we'll see is an overall reduction in the two, or an increase where they are in phase. If a wave is not completely out of phase, i.e. not 180 degrees out, some places they will add, some places they will subtract, resulting in a rather disjointed third wave produced here. So adding our displacements together at each point here, adding our red and yellow waves together, will result in this blue wave. A third wave at a slightly different phase to the original two. So when we are looking at interference, here we can see the phase and we can see the product of that phase. Here we're looking at a phi of 0. A phase of 0 means the two waves are exactly in phase. Here the orange line plus the green line will result in this purple line, essentially a wave twice the amplitude of its components. Here we're looking at the orange line plus the green line, y1 and y2. If these are now pi radians, remember 2 pi is one complete cycle. Here this could say phi is equal to 0, or phi could equally be equal to 2 pi. They're essentially saying the same thing. That would be one complete cycle. Here at phi equals pi, they're completely out of phase. If we sum the amplitudes of these two waves, we will end up with 0. In this case, here we're looking at phi as 2/3 pi, very similar to the previous example. If we add our green and orange waves together here, we will result in an overall reduced amplitude wave. So when we deal with interference, we're going to deal with a slightly simplified case so as we don't end up having to solve a problem that takes several weeks. So we'll look at waves with the same omega and frequency, k, lambda, and essentially amplitude. Both are traveling in the positive x direction. They're going to differ by some phase angle phi. So those waves will be said to be out of phase with one another by phi. The sum of the two waves here essentially will be y1 x of t plus y2 x of t. The resultant wave, if we define one wave moving along a string, so one wave will be given by y sine kx minus omega t, and the second wave will have a slightly different phi. So here we said had all the same values, so y2 will be our amplitude times sine kx minus omega t again in our term, plus some new phase. And this is always the best way to define these. Take your original equation, sine kx minus omega t, for one of the two, and then add an extra phase for the second case. Now if we add our two equations together, we'll have y sine kx minus omega t plus y sine kx minus omega t plus a phase constant phi. Now adding these together simply is a little bit trickier than it looks. The best way to do this is to actually apply a trig identity, and this is a case of knowing to apply this identity at this point. So if you go to the back of the book, or you just look online for a simple trig identity, you'll find that sine alpha plus sine beta here, these two terms added together, will be 2 sine 1/2 alpha plus beta times cos 1/2 alpha minus beta in this kind of expansion. This means that y prime, the new amplitude of these two waves, will be 2y cos 1/2 phi sine kx minus omega t plus 1/2 phi. So essentially, all we've really done is say that one wave is 1/2 of a phase out compared to the other. We'll end up with a cosine result here and a sine result here, coming from this particular equation. So the final wave will just be essentially a wave differing in phase constant by 1/2 phi, and with an amplitude of 2 times the amplitude times cos 1/2 phi. So if we look at a case where phi is equal to 0 radians, or of course 0 degrees, our two waves are essentially in phase. So this means y prime, our new amplitude, will be 2y sine kx minus omega t. So let's take a look at a problem that involves two interacting waves. So if we have two sinusoidal waves, so two sine waves, and they're set up in a string, as per an example we've seen previously with two people flicking a string, and they're defined by these wave functions. Y is equal to 2 sine 20x minus 32t, and y2 is equal to 2 sine 25x minus 40t. We have displacements and x values in centimeters and t in seconds. Part A wants to know what is the phase difference between the waves at x equals 5 and centimeters and t equals 2 seconds. Well, we can find the phase shift between these two waves by subtracting the phases of our two waves, phi 1 minus phi 2. This will give us 20 minus 32 minus 25 minus 40, essentially our phi terms. If we collect our terms together, delta phi will be minus 5 plus 8. That means we're essentially subtracting our two phi's, so phi will be negative 5 plus 8 times 5 plus 8 times 2, or 9 radians. If we're at 9 radians, this will be 516 degrees. Now, of course, that's quite a lot. So if we look at 516 degrees, this will wind up giving us 156 degrees if we look at how many rotations we're dealing with. The second part said what is the positive x value closest to the origin for which the two phases differ by plus or minus pi at t equals 2. Well, our sine function is going to repeat every 2 pi, so a phase shift of plus or minus pi will exist whenever delta phi is equal to pi plus 2n pi, and that'll be true for all integer values of n for us. If we sub into our phase equation again, then the smallest case will be x plus 2n pi, which is equal to minus 5x plus 8t. So at t equals 2, we will end up with pi plus 2n pi, which essentially will be 8 times 2, or 5 radians per centimeter times x will equal 16 minus pi minus 2n pi radians. So pi plus 2n pi will give us this. Now we have to say at 2 seconds, substituting in for 2 seconds, we'll have this. The smallest possible positive value of x at n equals 2 will be x is equal to 16 minus 5 pi radians over 5, which will give us 0.0584 centimeters. Another case of waves is looking at what's referred to as a standing wave. And this is the kind of thing we saw with that Tacoma-Narrows bridge problem that we talked about in oscillations. Here we have a string which is essentially tethered at both ends. If this string is flicked, the wave will travel down this line and then essentially back again. This will then superpose with itself and give two identical waves traveling opposite directions. As that occurs, we will end up with what's referred to as an antinode, a point of maximum displacement, and a node, a point of zero displacement. Our usual equations for waves apply, such as 2a sine kx here. So the wave function for a standing wave will be that the displacement y, essentially the displacement, will be equal to 2a sine kx cos omega t. And this applies for any standing wave. And you can see this result is very similar to one for an interfering wave system. And this is for the wave function of a standing wave for two identical waves traveling opposite directions. Because this is a sine function, you can say where you will end up with nodes, i.e. where you will end up with points of zero displacement. So the nodes will appear at points of kx here, which are equal to 0, sine of 0, essentially 0, pi, 2 pi, and 3 pi, etc., etc. The reason being that k, of course, our angular wave number, is 2 pi over lambda, over the wavelength. Here is our wavelength, and here essentially is our nodes. So we can expect to see nodes at 0, lambda over 2, 3 lambda over 2, blah blah blah, for any value, integer value of n. These are the nodes. The antinodes, these are the points of the greatest displacement from the equilibrium, here in case of an amplitude of 2a. The antinodes are at positions for which the coordinate actually satisfies sine kx being plus or minus 1. So kx will be pi over 2, 3 pi over 2, 5 pi over 2. So the antinodes will be at lambda over 4, 3/4 lambda, 5 over 4 lambda, etc., etc., etc. 1, 3, 5, 7, etc. So if we were to look at our standing wave itself. Our nodes are here. Our antinodes, as we're explaining here, will be at these locations. So in a very similar case to what we saw before for two interacting waves, we can see our standing waves interfering. So let's take another look at two waves interacting. In this case, two waves are traveling in opposite directions and producing a standing wave. We've got two wave functions, y equals 4 sine 3x minus 2t and y equals 4 sine 3x plus 2t. X and y are in centimeters again, and t is in seconds. Find the amplitude of the simple harmonic motion of the element of the medium located at 2.3 centimeters. So what have we got to work with? We've got two wave functions, which I know everybody loves. And these are absolutely identical apart from their direction of travel, y1 being a negative value, y2 being a positive value. So we can use y equals 2a sine kx cos omega t. This will give us 2a sine kx cos omega t equals 8 sine 3x cos 2t. We want the point where x is equal to 2.3. So if we substitute in, we'll have 8 times sine 3 times 2.3 radians, which will give us 8 times sine 3 times 6.9 radians. This will give us 4.6 centimeters, or 4.6 times 10 to the minus 2 meters. The last part wants us to find the positions of the nodes and antinodes if one end of the string is x equals 0. That means we're setting up a coordinate system probably at the left end of the string at x equals 0. And we want to find the positions of the nodes. We can't just do this outright. We are going to have to look at the wavelength of the travelling wave. So if we take k is equal to 2 pi over lambda, we know this is equal to 3 radians per centimeter. Consequently, lambda will be 2 pi over 3. We can now use our equations for the position of the nodes and exploit these. So x is equal to 0, lambda over 2, lambda 3 lambda over 2, blah 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 for n equals 0, 1, 2, 3 for the nodes, and for the antinodes, lambda over 4, 3 over 4, 5 over 4, etc. that we saw before. That means the nodes will be located at n times pi over 3 centimeters for these values of n, and the antinodes again at n times pi over 6 centimeters. So x will be n times lambda over 4 and x n times lambda over 2. So in dealing with our standing waves, we can look at our waves travelling in opposite directions such as this. The two waves will interfere and give us nodes and antinodes in each case. Here we're looking at the case at the beginning, t equals 0. After t equals our period divided by 4 here, a quarter of a period, we should expect to see essentially a flat line as our nodes and antinodes coincide and give us 0 displacement. At period over 2 here, we can actually see our interaction is essentially repeated again now, but here we've got node, antinode, node, antinode. So this essentially is the opposite of the case at t equals 0.